In example 16, we are told that the function of x is defined by x squared minus 3, and x is a real number, and x is supposed to be greater than or equals to 0. Somebody wants us to find the inverse function of fx in part A. And as you are used to, this one generally, because it is written in terms of y is equals to x cubed, not cubed but squared, x squared minus 3, you interchange the variables and have x is equals to y squared minus 3, and then our interest is to make this y the subject of the formula, which says that y squared is equals to x plus 3, and the root of both sides will give us y is equals to the square root of x plus 3. And finally, this is simply the inverse function of fx. X, the root of x plus 3. Part B of the question is asking us to sketch y is equals to f inverse x. It's rather y is the inverse of x and states its domain. What we need to understand is just one truth, that that the inverse function is a reflection of the original function along the mirror line. Y is equals to fx. So if we can sketch the original function, which talks of and y is greater than, if we can sketch the original function like this, let's say like that, let's have the first domain x being equals to 0. Substituting over here, we have 0 squared 0 minus 3, then we have the very first value of y to be minus 3. When x is a 1, 1 squared is 1 minus 3 gives us a minus 2. When x is, this is 1, 2, 3, 4, 5, moving forward. When x is a 2, 2 squared is a 4, 4 minus 3, we get, let's talk about, this is minus 1, this is minus 2, we have 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1. When x is a 2, then you can already see that y is a 1. What about when x is a 3? 9 minus 3, which is a 6. So it shoots up suddenly and the graph looks like that. And as you can see, this is basically the graph of y is equals to fx. There is a reflection along, there is something that we need to remember, that if this is y is equal to fx, then we must remember there is a line of reflection that is along this particular line. That is along this particular line, y is equals to fx. That means our new inverse function graph is going to pass this particular point, and this point will be reflected along this line. It becomes this, it comes to this particular point. This point is going to be reflected to itself, and this point is supposed to be reflected to itself, and it gets to minus 3. Let's see, minus 1, minus 2, minus 3. there is a reflection of this point to this point. Then this point, there's a reflection of this point to this point. So you're going to have something that looks like that, and you will call that the y is equals to the inverse function of x. This is the line of reflection, which is y is equals to x. You do not have, but even if you wanted to plot it, you would use you will use the first domain, or rather the range. The range is, when the domain is 0, the range is y is greater than or equals to -3. So if you use this one to be the domain of the inverse function, you will realize if you put it over here, that -3 plus 3 is 0, and the root of 0 is basically 0. When x is a -3, you will find that y is going to be 0. Moving forward, when x is 0 here, the root of 3 is something less than 2, and that is it. So we are still on the right track. But I didn't want to substitute in the functions like we did in example 15. I just wanted to show that the inverse graph can clearly be sketched after reflecting the original graph of the graph of the original function along the line y is equals to x. But it is part C that we must take care of. Part C that we must take care of, because if we come over here and talk about part C says solve the equation fx is equals to f prime x, or rather the original function is going to be the inverse function. And as you can see, the graph shows us that point very clearly. It is this point when the two graphs are agreeing. They are speaking the same language. The value of the fx is the same as the value of the inverse of x. So this particular point, the point of intersection. And what is the x coordinates of that particular point? Because we are talking about y is equals to x. Meaning that this is giving us just one insight, and you're supposed to understand that fx is going to be equals to x at this particular point, because along this point, any point along this line, y is equals to x. So whatever the value of y, because this is y, is supposed to be equals to the value of x. So in this case, whatever the value of y is going to be the value of x along this point. So this one is very important, remember that. But what is our original value of fx? Our fx is, meaning that x squared minus 3 is equals to x, because y is this particular function according to the original function of x. What does that mean? That x squared minus x minus 3 is equals to 0. And therefore, we just have that quadratic equation to solve. And it's already showing that if you want to have x is equals to 1 because of minus b, plus or minus 1 squared, which is a 1, minus 4 times 1 times minus 3 all over 2 times 1 because of 2a. This is something which you are familiar with. So x is 1 plus or minus the square root of 1 plus 12. That means the square root of, because this one is going to be minus negative 12, so everything under the square root becomes 13 over 2. So if you specifically want to give the values of x, you can talk about you can talk about x being equals to 1 plus the square root of 13 everything over 2. And why have I said that? Because already you can see x is supposed to be greater than 0, so we cannot take the negative aspect because that will not satisfy our conditions of the original function. So yes, there could be two values, but according to the how our question is set, this is the only possible value of x when the function of x is equals to the function inverse of the same x. And that is just like it. As far as example 16 is concerned, that is what we need to understand. Okay.